Hey everyone, it's Mr. Lambert with your lesson and notes for Tuesday, February 16th, 2021. We are into our 3C standards, and today we're going to be dealing with 6.AF.9. So one of the things we need to be able to do is to make tables of equivalent ratios. A ratio is just a number compared to another number, and these will relate to quantities with whole number measurements, and find missing values in those tables. And then once we have those values, we're going to be able to plot those values on a coordinate plane. This is all dealing with something we call functions. So we should probably, first of all, define what a function is. So I would grab out your math journal or your three-ring binder, go to your math vocabulary section and add this term to it. We're going to have a couple of terms that you will need to add today. So the first one is a function. The function is a relationship that assigns exactly one output value to one input value. So you put something in and you get only one thing back out. So since it's only one thing in and one thing out, the function at the end, if we have one input, it's only going to have one output. And these are going to look like algebraic expressions. I'll show you how here in just a second. The function rule then, and you'll need to add this term as well. The function rule describes the relationship between each input and output. So for every input you put in, you get an output out. And the rule tells you how you get between one and the other. So what does that look like? Well, we'll use it with this problem. So it says a ruby-throated hummingbird beats its wings 52 beats per second. If you haven't seen a video of this, it's pretty cool. Think about it. Each second I could count to 1. Well, there's 1 second, and in that tiny amount of time, this bird will have beat its wings 52 times. So we want to make a table showing how many times the bird could beat its wings in, say, 2 seconds. Well, we can use what we know. We can take the number of seconds. We'll call that S. So that will kind of be our variable. Then we take our S and multiply it by the number of beats per second. Well, which would be 52, and that would give us our total number of wing beats. In this particular set, this is what we call a function table. So here we have our input function, we have our output function, we have our number that we're going to put in, we have our function. This is the relationship between the two numbers, and then our output is going to be the thing that we get out of it. So in this particular one, get my handy dandy writing tool here. The number of seconds we said is 2 seconds, right? So our S in this case would equal 2. So we'll take our 2 and we'll plug it in for the S. 2 times our 52 beats, and that is going to give us our total number of wing beats. And 52 times 2, well, 2 times 2 is 4, and of course 2 times our 5 is 10. So we would have 104 beats in 2 seconds. There we go. As you're working with these, you'll have two different things. An independent variable, that's your input. That's the number that you're putting into the function. And the dependent variable, which comes out. That's the output of that function. So if I go back and look at this, our input in this case, our dependent function was the 2. That's our independent function our independent function, the function that we put in was our 2. That's the one that we put into our function. And then the output that we got, our dependent variable, that was the 104 beats per 2 seconds. So there we go. The independent variable is the number that we put into it. It's the number that can change. And then the output is the dependent variable because it's dependent on what the variable going in is and the function itself. So you will need to know those two terms. I would also write those into your binder. Go ahead and pause the video, because at the end, of course, I'm going to ask you to take a video or take a picture of these vocab words so I know that you've worked along with us today. So you'll need to know independent variable, the input value that goes into a function, and the dependent variable, that's the output value that comes out of the function. All right, So let's work with some more of these. So here we go. It says, make a table to show how many times this bird will beat its wings in 6 seconds. So same deal. We'll put in our independent variable. In this case, we want to know for 6 seconds. Our function doesn't change, but we're going to place our 6 in for s for the number of seconds, and then multiply that by 52. And of course, our output, our dependent variable, will be the answer to this function. So if I put in 6, my output would be 6 times 2, which is 12. We carry a 1 over. And then 6 times 5 is 30, plus 1 would give us 31, or 312 beats in 6 seconds. There we go. Not too bad, right? Moving on. So let's say we want to go longer. Could we figure out for 20 seconds? And we can. We're just going to follow the same thing. The only thing changing here initially is going to be our independent variable, which will be 20 in this case, because that's the number of seconds we want. We're going to take that 20, that independent variable, and plug it into our function. So our function rule is we're going to take our independent variable, which is 20, and we're going to multiply it by 52. Same deal, guys. 0 times 52 is 0. That's easy breezy. And for here, 2 times 2 is 4, and 2 times 5 is 10. So 1,040 beats in 20 seconds. There we go. It's as easy as that, guys and gals. Just taking that independent variable and then figuring out how the function changes at the end. Okay, so here's something that's a little bit different. A giant hummingbird beats its wings only about 10 times per second, so much slower. Make a table to show how many times the giant hummingbird can beat its wings in 3 seconds. So again, we'll have on our function table, we'll have it set up so that we have whatever our independent function or our variable stands for. In this case, the number of seconds, which will be s. We have our function rule right in the middle. So we're going to take that independent variable and multiply it by 10, since it's 10 times the number of seconds. And then that will give us our dependent variable or our output, which will be the number of wing beats. So in this case, we would take the number of seconds, which in this case is 3 seconds. We want to know. So we're going to plug the 3 in for our s, so 3 times 10. And of course, 3 times 10 will give us our answer of the number of wing beats. It would be 30. Easy breezy, right? So let's look at a couple more examples. So let's say the output of a function is 7 more than the input. And it says complete a function table for this relationship. So the function rule is x plus 7 because the output is 7 more than the input. And what we want our input to be the thing that can change, our independent variable. So we're going to take that independent variable, add 7 to it, and that will give us each output. So again, our function table would look like our independent variable on the left, our function rule then comes here on the right. Make sure on the left we're defining that independent variable. Our function rule right in the middle, and then our dependent variable will come out on the right side, just like with our other function table. So in this case, if we input all of these, let's say our input is 10. We'd add 7 to it, of course, and get 17 for our output. Same deal, if our input was 12, we would just add 7 to that 12 and get our output. Our dependent variable would be 19, so on and so forth. Similarly, sometimes you're going to get the output. You're actually going to know your dependent variable first, and then you're going to need to work backwards to find that independent variable. So, in this case, my outputs I know. My input is my function rule is 3 times whatever my input variable is. So I know 3 times something should give me 6. I know 3 times something should give me 15, and 3 times something should give me 21. And in this case, we can just do what we've done previously using our multiplicative rules of equality, and we can go back and divide by the number we're multiplying by, and that should give us our input number. So in this case, 6 divided by the 3, well, that gives us 2. 15 divided by the 3, and we know that goes in there then is 5. So I know that that guy would roll in here. And same deal, I know 7 times 3, or 21 divided by 7 would give me 3. And I work backwards that way. So ladies and gentlemen, just like we can work forward, we can work backward, especially since we know those properties of equality, and balance the equation to find what our input or our variable equals. That's part of the reason why we've learned how to balance those equations. All right, one last one to look at, and then, ladies and gentlemen, we'll let you get on with your day. All right, so question number 4. Our last example here, it says the Gomez family is traveling at a rate of 70 miles per hour. The function rule that represents this situation is 70x, or 70 times x, where x is the number of hours. Make a table to find out how many hours they have driven at 140 miles, 280 miles, and 350 miles. Then graph the function. So not only are we going to fill in the function table this time, but we would graph the function. So in this case, what we know is we know our output and we know our rule. So we're going to work backwards like we did before, and we are going to balance the equation to find the input. So as it shows here, we just divide each output or each total, our dependent function, by 70, and that would give us our independent function. It's basically the inverse of our rule, or the opposite of our rule. So if we did that, our outputs for the 140 miles, dividing that by 70, we would get 2 hours. For 280 miles, that would be 4 hours, and for 350 miles, if we divided that by 70, we would get 5 hours of driving time. And then we would graph those on our chart here. Now, remember our x and y axis on a coordinate plane, the x is the left and the right value, and our y is at our up and down value. And since we have put an x and a y into our input and output here, with our problem, we can actually graph this as a line. So for my input, for 2, I would go to 2. So that's my x input, or my x value, so I would go to the right 2 spots. And then I would go up, or my y input, my y value would be 140. So 2 comma 140, so 2 over 140 up, that would be my first data point. My second would be for 4 hours, my data point is 280. So I would go over 4 and then up to the 280 mark. And then last but not least, for the 5 hour mark, I would go over 5 to the right and then up 350 to match my data point here, and I would plot the thing. Now, at the end, the cool thing about this is if I have at least 3 data points and I can draw a perfectly straight line between the 3, anything that falls on that line is actually something, an input and an output, that work for our equation. This is why we call these linear equations. Linear means a line. So there you go. By plotting these, and they should all be in a straight line. If you see 3 of them and they're not basically in a straight line, you know you've probably got a problem with this type of linear function. All right, so there we go. That's what we have for today. Hopefully that was pretty easy for you. I'd like you to try the independent practice problems, the guided practice problems that are posted right below. And when you're done with that, the independent practice is for you today. If you got any questions, please make sure to let me know. Other than that, I hope you have a great day and good luck.